Greetings. So glad you could join me today. So there's a spot in AP Calculus that you get to during integration where you're asked to begin to find some things like the area between two curves or the volume of a shape using cylindrical shells or using washers or discs. And in that section, the ones with the volumes, there is a subject that has you find the volume of a solid by knowing the base of the solid and then knowing what the cross-sectional area is of the solid. So that if you took and you cut the solid in a particular way and you looked at the shape that you got on the face of where you cut, it would look like a particular shape. And you're asked to use this information to find the volume of this shape. And this has always been a fairly difficult section for many of my students. I'm going to show you that there's some key things about this type of problem that actually make this problem very doable. So we're going to jump in and we're going to take a look at some of the techniques that you need for this problem and be able to solve any problem that comes your way using these tools. So usually what we would be asked is to find the volume of a solid that's on a particular base, and the base is described by some sort of shape or an equation. So we're going to take the solid of our shape as an ellipse. So we're going to write out the equation of ellipse. And this reduces to x squared over 9 plus y squared over 4 equals 1. And this is going to give us an ellipse. Let's draw out a coordinate plane. Let's draw this out real fast so we know what we're looking at. So we have this ellipse, and I know that the number below the x squared is going to tell me how far to the left and to the right I go. So it's going to go 3 out to the left and to the right. 3 squared is 9. And then the number below the y squared is going to tell me how far up and down. So it's going to tell me to go up and down 2. And there we have the bounds for our ellipse. So there's our ellipse, and if we were to slice it, we could imagine that this is sort of like an egg shaped, but it's got a flat bottom, and we're going to slice it down, wherever. Doesn't really matter where we slice it. So let's say we slice it right here and we pull it apart. We're going to see an equilateral triangle. Let's say it's an equilateral triangle. It could be any of a few different shapes, and that's one of the keys that we're going to be talking about, is that the cross-sectional areas can only be a small selection of shapes. And to give you an idea of what this is going to look like three-dimensionally, I'll draw this out, as it were, at an angle here, sort of pushed over so that you can kind of get a better idea of what we're looking at. So there's our ellipse. And then if we look at that cross-sectional area again, then it's going to be a triangle that looks something like this. So this will be an equilateral triangle. And if we keep slicing, we're going to have bigger triangles until we get to the axis, and the triangles get smaller again. But this is what we're looking at. So we've got all of these triangles here. And we're asked, using these triangles, can we come up with the volume of this shape? So you can imagine that we kind of get this like egg shape here. It's kind of got this edge around it. The first thing we're going to do is we're going to talk about the 5 different shapes that would be involved with finding the volume of one of these solids. The reason why there's really only 5 is because when you look at what we have to work with, we only have one side of the shape to work with, and we're asked to talk about the area of that shape. So that limits us to how many different shapes that we can use to find the area of. So the first shape that we can find the area of by knowing just one side is the square. Nice and straightforward. We say that this side length here is S, and so the area of this square is just S squared. Okay. What about a right triangle? Specifically an isosceles right triangle. Isosceles right triangle is really nice because in this case, the base and the height are our legs, and the hypotenuse comes down at an angle like that. And we know, well, we can call this side S, and the area for any triangle is 1/2 times the base times the height. And the height and the base are the same because it's an isosceles triangle. So this tells us that the area of a right triangle with the leg on the base is 1/2 S squared. We could have an isosceles right triangle with the base being the hypotenuse. So let's draw that out. And here we'll still be able to find the area of this, even though it may not look like we'll be able to. But because this is an isosceles right triangle, we get some properties of the triangle that make things really nice. Like the first thing is if I drop down the altitude here in this triangle, then the altitude also acts as the median. So it cuts the base into 2 equal parts. So I'm going to call the base of this triangle, I'm going to call it S. And what I need is the height of this triangle. So I need the length of this line right here. And if we look at what this altitude has done, it's broken up the 2 triangles into right triangles as well, because this is a right angle because I've drawn the altitude. And because it's an isosceles right triangle, this angle right here is equal to this angle right here. And since that's the case, and this is a right triangle, this must be 45 degrees right here, and then the other one also has to be 45 degrees. That means that the 2 triangles that I made in here are also isosceles right triangles. And so since this is half of the base length down here, then this height right here must also be half of the base length. Okay, great. So now we can find the area. So it's 1/2 times the base times the height, and the height is 1/2 S as well. So putting all that together, we get the area is equal to 1/4 S squared. And I'll leave off that square right there. Okay. So there's one more triangle for which we can find the area of by knowing just one side. And that is an equilateral triangle. We're going to split this equilateral triangle into 2 equal parts. So we're going to drop down the altitude here. And I know that this is going to make a right angle. And because this is an equilateral triangle and so it's also an isosceles triangle, that means that the side lengths down here are going to be split into 2. So these 2 are going to be equal. Okay, so what else do I know about this triangle? Well, let's see. Since it's equilateral, I know that this angle right here is 60 degrees. And because it's isosceles as well as equilateral, this angle up here is half of that. It's 30 degrees. Okay, so now this side length of this triangle is S. That means this length right here is 1/2 of S. And if we remember from your right angle trigonometry, the lengths of the sides follow a particular pattern. Sometimes you may learn that it's like 1, 2, rad 3, something like that. Or you can use, the fact that you know the opposite side to 30 and you know the hypotenuse, and so you can use the Pythagorean theorem to find the other length. So I'm just going to write it down. It's rad 3 over 2 times the side length. So the area for this triangle is equal to 1/2 times the base times the height. So it's rad 3 over 2 times s. And so put everything together, and we get rad 3 over 4 s squared. Okay. So there's one more shape. There's other shapes to work with too, just that these ones are always the ones that are being used in these types of problems. But there are ways to come up with other shapes that you could find the area of just by knowing one side. But these are by far the most common. So the last one we'll talk about is the semicircle. The semicircle is going to have a diameter of s. And so that means that the radius is just 1/2 of s. So the area of a semicircle is just half of a circle. So it's 1/2 times pi times the radius squared. So the radius is 1/2 s squared. So putting all this together, we get 1/2 times 1/4, because it would be 1/2 squared. So that's going to be 1/8 times pi. So I'm going to put that all together and turn that into pi over 8 times s squared. So there we have it. There are the 5 different shapes that you can find the area of just by knowing one of the sides. And we're going to use the equilateral triangle with our shape here, with our ellipse, to find the volume of a solid whose cross-sectional areas are equilateral triangles. Well, when you learn about integration, one of the ways that you explore it is to think about the fact that it adds up things, right? So one of the things that you learned was that the integral of a function between two different points, a and b, and you got this dx in here, which we'll talk about a little bit, is equal to the limit, and we'll use the n goes off to infinity definition. The limit is n goes off to infinity of the sum of function values evaluated at particular x values times this delta x, or sometimes you see it as delta x sub I. And the summation runs between I equals, usually it's 1 or 0, all the way up to n. And so an integral is essentially, in this way of looking at it, a summation. And what is it the summation of? Well, in this case, it's the summation of y values, right, because that's what a function is, times these delta x values. So if we were to go quickly to look at, kind of explore this for just a second, we can take a function. Let's just draw out any function, and you've seen this in your book. And here's an a, and here's a b. And then here is an x sub I. And that x sub I gets taken up to the function here, and it makes a line. And this delta x sub I gives you a little neighborhood around that x sub I value. And so if you look, what we end up with here is a rectangle. So I can take different x sub i's. Well, there's an x sub I there. You can take another one here. And again, you get another function value, and you get a little neighborhood, and you get a rectangle there. And so this summation now is the area of a rectangle. And you are summing up all of these rectangular areas. And then the limit basically tells you to decrease that delta x, that little tiny neighborhood around the function, take that all the way to 0. So essentially you're adding up the areas of a whole bunch of lines, but because of the way the limit works, you're able to get an actual number out from it. So one of the ways that we can look at an integral is a way of adding things up. And we can add up a lot of different types of things. Let's think about a potato. Take a potato. And a potato, we can do a lot of things with a potato, right? We can make a baked potato out of it, make French fries out of it, or we can make chips. So to make chips, we would take and start to slice this potato up into very thin pieces. So we got a little potato chip there, and then we get a little potato chip there, and so on. And we could take this potato and make it all into chips. And the potato then would be all of these little chips that have this area and this very thin thickness. And if we found the volume of the potato as it was, and then we found all of the areas of these chips and multiplied it by the width of each of the chips, right? Because each of these chips have a thickness, they would give us, and we add up all of those areas times those thicknesses, they would give us the volume. Those would be the exact same thing. So we can look at this as an integral problem. The volume of this potato is equal to the integral from the left end to the right end. And what is it the integral of? It's going to be the integral of the area of each chip times the thickness of the chip. And if we made each of these chips infinitesimally thin, then we would get the exact volume of this potato. So it's just like with the volume of our solid. When we look at the volume of our solid, we're going to be doing the exact same thing. And you've done this already a little bit if you've already studied cylindrical shells or using washers or discs. So the volume of our solid is going to be equal to the integral from A to B, and we'll talk about what A and B are in a little bit, of the area of each triangle times the thickness of each triangle. Now we can begin to actually put in some values for what we have here. Still going to leave the integral from A to B. And we know the area of the triangle because we're dealing with equilateral triangles. So the area of the triangle of each triangle, whatever it ends up being, is rad 3 over 4 times the side length squared. And then the thickness of each triangle, that's where our dx comes in. So if we go back up and look at our shape here, we would need to figure out how to come up with the area of each of these triangles and then multiply it by its infinitesimal width. So you'll notice that in our integral that we have two different variables, right? We have s, which is our side length, and then we have x, which is our infinitesimal thickness. So we either need to change the x into s's or the s's into x's. And it's going to be a lot easier to change the s's into x's. So what does that exactly entail? So our task first is we want to write down the side length as a function of x. So how are we going to do that? Well, let's take a look at what we've got here. So we've got our ellipse, and we need to be able to take any x value here. So we've got the pink line there already. So I'm going to just take that x value right there. And then I need that to give me a side length, really from there to there. But if we can go from the x-axis up to where the ellipse is, that would be useful as well. So that's what we want to do. We want to take an x value, plug it into something, and then come out with a y value. But what do we have that would give us the opportunity to come up with such an equation? Well, we've got the ellipse, right? We could solve this ellipse equation for y, and that would give us an equation for which we could plug in an x value and get out a y. So let's do that. So the first thing I'm going to do is I'm going to move the x squared over 9 over by subtracting it. And so I get y squared over 4 equals 1 minus x squared over 9. A couple more steps here. Multiply both sides by 4. And we get y squared is equal to 4 minus 4x squared over 9. And then the last thing we're going to do is we'll take the square root of both sides. Just remembering that when we take the square root of y squared, we get a plus or minus involved. So it's plus or minus 4 minus 4x squared over 9. So that plus or minus just tells us that we could either go to the top or the bottom of the ellipse. And we're going to go to the top of the ellipse. So we're going to take the positive side. So now we have this really nice equation that will give us a y value for whatever x value we plug in. So y equals 4 minus 4x squared over 9. That's not my side length, but we're almost there to our side length. The y value here just goes from the x-axis all the way up to the ellipse. And the side length is just double that because the ellipse is centered at 0, 0. So let's find s. So s is equal to 2y. So s then is going to be equal to 2 times the square root of 4 minus 4x squared over 9. Okay, so now let's get it into the integral. So the volume of our solid is going to be the integral from a to b. Now a and b are the left end and the right end of our ellipse. So if we go back up to our ellipse real fast, you'll see that the ellipse goes from -3 to 3. And so that's where we're going to take our ellipse, take our integral from, -3 to 3. And remember that we're taking the area of each triangle, and then we're going to be multiplying it by the thickness, which I'm just going to go ahead and call dx right here. So our volume is going to be the integral from -3 to 3, and our area of each triangle is rad 3 over 4 s squared dx. And then let's go ahead and plug in for s. And I realize that we could go from 0 to 3 and double the integral. That's fine if you want to do that. There's no problem in doing that, but I just going to keep the complication to a minimum. So now we're going to plug in what we had for our s value, which is 2 times the square root of 4 minus 4x squared over 9. And that's all squared. So now let's start evaluating this. So v equals the integral from -3 to 3, rad 3 over 4 times 4 times 4 minus 4x squared over 9. So that square gets distributed to both the 2 and the square root. And there we go. So the next thing I'm going to do is I'm going to go ahead and combine the rad 3 over 4 and the 4 because those are next to each other. Rad 3 times 4 minus 4x squared over 9 dx. And then the next thing I'll do before I integrate is I'll go ahead and distribute this rad 3 into both terms. Dx. Okay, so let's integrate all of these. And if you're still a little new to integration, that's fine. You can use the power rule and work through this. The integral of 4 rad 3, well, that's just the integral of a constant. So that is going to be 4 rad 3x minus, we've got the 4 rad 3 over 9 times, and then we'll take the integral of x squared, which we add 1 to the exponent and then divide by that new number, that new exponent. And then we're evaluating this from -3 to 3. So the top number goes in first. We're going to evaluate all of this at 3 first. So 4 rad 3 times 3 minus 4 rad 3. I'm going to go ahead and multiply the 9 and the 3 together to get 27 times 3 cubed. We'll take all of that. And then we'll subtract away, plugging in the bottom number. So we get 4 rad 3 times -3 minus 4 rad 3 over 27 times -3 cubed. So we've got V equals 4 rad 3 times 3. That's 12 rad 3 minus, well, this is nice. Rad 3 cubed is 27, so 27 and 3 cubed cancel, so we get minus 4 rad 3. And that'll be all together for the first one. And then for the second collection, we have 4 rad 3 times -3, so that's -12 rad 3. And then we have a minus, and then we get the minus from the cubed, and the 27, those cancel, and so we get plus 4 rad 3. Let's combine all of our terms here. Everything's got a rad 3, so we just need to add up everything correctly. So we have 12 rad 3 minus 4 rad 3. That's 8 rad 3 minus, and then minus 12 rad 3 plus 4 rad 3, so that's -8 rad 3. One last step, we get 16 rad 3 because we're adding those together. And there we have it. There's the volume of our shape. So this all the way back up here. So the volume of this shape ends up being 16 rad 3. And you can use this technique to answer many of these, almost all of these types of questions in your book. Some of them take a little bit more effort, or some of them have a little bit more of a clever approach. But in general, this is how you're going to answer these questions.